will be here as a postdoc, working as a ayudante doctor with this academic course. He has worked on granular media, these kind of things. So welcome. Another new postdoc is, well, it's not really new. Gianluca Giorgi has been here for some time. Now he will be working with Roberta Santini and other people in the Food Drugs project on quantum systems and quantum synchronization. So welcome again. And also, this is Ali Hossein Shirazi. So I don't pronounce well the name. He was well there. He is from Iran. He will be working with Claudio in LCS analysis of neuronal systems. So welcome. He will be here at least until the end of this year. Now, so Tomás is not here. So there is another new postdoc, but he will introduce other times. So welcome everybody. And this is the new seminar.
Yeah, good morning everybody. It's a pleasure for me to introduce you Alireza Valizadeh. He's from Iran, from the north of Iran.
This is the, I will introduce the new postdoc, Tomás Duane. He's coming from Toulouse, if I remember properly, or Paris. He was working on the first internoia on urban mobility with Maximilian and other people in Norway. Welcome.
Well, I told you that today we have Alireza Valizadeh here. He is from Iran. He got the degree in electrical engineering, then he realized that was not what he wanted. So he did a PhD studying physics in the Institute for Advanced Studies in Basic Science in Zanjan. It's about 300 kilometers north of Tehran. At the time he was working in synchronization of Josephson junction. But after some time he got a PhD fellowship there in the same institute, and he started to work in computational neuroscience or model of neuronal dynamics, things like that. And since 2012 he's assistant professor in Zanjan, and for a short period in 2013 he was visiting Zanjan in the rural university in Bochum in Germany. And his main research topics include synchronization in neuronal system, brain rhythm, and today he's talking about the communication delay in coupled neuronal systems. So, Ali, thank you very much for being here.
Thank you, Claudio. So I'm very happy of being here. I don't need to say that Mallorca is a very nice place, but it's also a warm place. But interestingly, it has warm and nice people as well. So I'm happy of being a very active research group here. So thank you for letting me to present my work here. Actually, I have an irrelevant introduction to my work. And I don't know if I should switch it on.
Sure.
And also this one. Thank you. Actually, it's about 10 years that I conduct courses from when I was a PhD student. So I had the chance to teach to undergraduate students. But nowadays, whenever I go to conduct a course, I have a level of stress after 10 years. And when I'm going to give a lecture in English, the situation is worse. So this is an excuse for me. For the man in cave, the stressful situation is maybe confronting with a bear or the tiger, and every science helps him for fight and flight. For example, faster heartbeat, faster breathing. You have some signs like trembling, dry throat, dry mouth, and none of them helps you for giving a lecture. Yeah. And nowadays, so maybe for civilized man, a stressful situation, maybe it's having an picture, having a date, and for the first time, and all of these times prevents you for having good efficiency. But I'm hopeful, not for myself, but maybe for our sons. Maybe sometime, if scientists are not so lazy as evolution, maybe after a few generations they can manipulate genes and match the needs of the human with this science. So, indeed, I assume that you are familiar with synchronization, most of you. So, I'm hoping that the first introductory part that I give here is useful for some of you. First, I say something about the possible functional role of synchronization in brain. Then I try to explain what is the role of delay in synchronization properties in neural networks, and I pose the notion of dynamical frustration when the connection between neurons are desynchronizing, and finally I say something of actually possible functional role of this phenomena in nervous system. Actually, in nervous system, generally, synchronization can occur in a system, in a network of oscillator, because of direct connection between the components. For example, you have heard maybe about the fireflies in a tree that they're synchronized, they're firing actually their lights with each other, they see each other, they feel each other, and they tune the rhythms of them actually producing light with each other. Other examples are, for example, clapping in a concert, or cardiac pacemakers in the nervous system, and many, many other examples. In this situation, the components of the system feel each other, are connected with each other, and they can tune their rhythms with each other. But synchronization also can occur without any connection between individuals. For example, a very common example is that the wake-sleep rhythm around the world. For example, two villages which are far apart, and people in these two villages have no direct connection with each other, but because of sun, they have a tuned rhythm of waking and sleep, which is 24 hours on average. Both of these mechanisms can be source of synchronization in brain system, which we will see later. So now I say something about the possible functional role of synchronization in nervous system. The first example is a very nice concept of seam fire chains. You know that in the nervous system, the connections are big. It means that if one neuron receives a connection from another neuron, firing of the source neuron is usually not enough to elicit an action potential in the target neuron. The connections are so weak in the nervous system. And if a target neuron wants to fire, it needs some, for example, several presynaptic, several source neuron to fire almost in synchrony to actually excite the target neuron. It means, here, consider that I have a layered network of neurons. The connections are feed-forward, are very simple configuration. Each neuron in each layer receives several connections from preceding layer and gives several connections to the next layer. So, if a neuron in this layer fires, it is not enough usually in nervous system to excite the neuron in the next layer. But if several neurons in one layer fire in almost synchrony, they can actually elicit an action potential in the neurons in the next level. So if I have a synchronized activity in one layer, you will see that all the layers can be active because of the active synchronous, almost synchronous activity of the first layer. So the data can be transferred reliably in such a system. Another possible role of synchrony is the so-called binding problem. Actually, if you have in your visual field, you have two objects. Consider that you have two objects in your visual field. Very simply, you can consider a red circle and a blue square. And both of them are present in your visual field. This is a very old problem in neurophilosophy. You know that different features of an object are usually coded in different regions of the brain. For example, color is coded in one region, and the shape of the object is coded in another region. So if you see a red circle, it means that the neurons which respond to circle are active, and the neurons which respond to red color are active. There is no ambiguity here. But if you have another object in your visual field, for example, a blue square, you see that the neurons which respond to blue color are simultaneously active with red, and the neurons which respond to square. So you see there is a confusion. Square, circle, red, blue, all the neurons are active. And how the nervous system knows that these are two objects, two entities. One of the actually proposals, it is not, actually it has not enough experimental support, but one of the proposals is that temporal binding. It means that two features of an entity, the neurons which respond to two features of an entity are active simultaneously in synchrony, and those who respond to another entity are active again in synchrony, and in this way brain knows that they belong to one entity. Okay, I hope that. So there is the so-called temporal binding. As I told you, it has not any enough experimental support, but again, it's logically a beautiful idea. Another functional role of synchronization is the so-called communication through coherence. Actually, brain rhythms are known from 100 years ago. Having a brain rhythm, alpha, gamma, say, all of them, they mean that there are some coherent activity of the neurons in one region. So there are some neurons in one region, they have some sort of coherent activity, and they produce a collective rhythm, a collective oscillation for that region. There are also some collective oscillation in other regions as well. So consider that there are two regions in the brain. It's not working.
It's not working anymore.
I can do with this. Suppose that these are two oscillation of two regions in the brain, and they are antiphase. And suppose that, for now, suppose that this oscillation now show the level of inhibition in the system. So when you are in the peak of the oscillation, it means that inhibition in the system is in the high level, so the neurons are less excitable. On the other hand, when you are in a trough or in the minimum, it means that inhibition is low, so the neurons are more excitable. If you have two regions, in this case, if the oscillations are almost in phase, if the neurons in one region spike, the effect of them reach to other regions in an instant that the neurons in target region are more excitable. So we can say that this region can excite this region in this case. But on the other hand, if the two regions have antiphase relation between each other, if the neurons spiking in one region, say here, the effect reach the other region in an instant that the other region, the target region, is less excitable. So this connection is effectively off, and this connection is effectively on. The speed that structural connections are present for both of these subsystems. In this way, actually tuning the oscillation of the regions with each other can make a dynamical channels for communication. You can on demand turn it on and turn it off. Now, actually to give an explanation how delay can affect the synchronization properties, I use a very simple example. A very simple example of two simple oscillators, just phase oscillators, which are connected to each other with so-called Kuramoto coupling. Let's see this, say this equation. Suppose that the first oscillator advances the second oscillator in some instant. So let's see what happens for this coupling term. If the first oscillator advances the second one, this term will be negative. And this is negative, so the rate of the change of the first oscillator would be smaller. Slows down the phase of the first oscillator. On the other hand, this term for the second oscillator, which is lagged, actually will be positive, and this accelerates the second oscillator. That's why I called such a connection as a synchronizing connection. It can be, with a simple mathematics, it can be shown that the stable state of the system is when the two oscillators are close to each other, they lock to each other with a small phase lag. And in this way, I say that this form of coupling are synchronizing. They are attracting in the phase plane, They want to two oscillators to get closer to each other. One other thing I should stress here, that these connections here are instantaneous. It means that the oscillator 1 sees the oscillator 2 at the same instant which we are studying the dynamic. If we consider, actually we enter delays in communication, the situation changes. Now, I'm using the same functional coupling terms, Kuramoto coupling term, the same two oscillators. Again, let's see what happens. The first oscillator advances the second, and it actually sends a signal to other oscillator that I'm ahead, go on, accelerate, speed up. But when the signal arrives in the second oscillator, the first oscillator may be in another situation, in another position. So suppose that that's here. So it says it has sent a signal to other oscillator, speed up. But if this speeds up, they will be more far apart. So it's sending, a wrong signal to other oscillator. Depending on the delay time and on the actually other parameters, the connection can be synchronizing or desynchronizing. It means that the connection can be attracting in phase plane or repulsive. Depending on that, the actually stable phase lag can be near 0 or near pi. That's why I say that delay can change the nature of the coupling. So, when delays are important, maybe it's very simple to think about it. Actually, you have a time scale in your network that most important time scale is the actually the period of the oscillation of the oscillator in your system. And if the delays are comparable with this time scale, delays are important. In the nervous system, there are experimental results that, you know that in nervous system you have a neuron, presynaptic neuron, the signals go along the axon, which has a certain time delay, then they should elicit postsynaptic potential, then again the signal should travel along the dendrites to reach to the target neuron. So there is a certain time delay between firing of the presynaptic neuron to elicit excitation in postsynaptic neuron. These delays, experimental results show that it can be from 1 millisecond to tens of milliseconds, depending on the, this is, for example, for average size animals. If you look at this range of the time delay, you'll find that they are important. They cannot be ignored because firing rate of neurons in the brain are ranging from, say, 1 hertz to 100 hertz. And if you calculate the interspike interval, I mean the period of the firing, you will see that this range of delays are comparable with the period of firing in the nervous system. So in the nervous system, we cannot ignore delays. The first example I brought was about the phase oscillator. I just reviewed that any oscillator, any complicated oscillator which has a limit cycle as a solution and has actually a periodic, near periodic behavior, it can be reduced to just a phase variable. With any complicated dynamical equation, you can reduce any periodically behaving oscillator to just a phase oscillator. But actually, the notion of phase can be generalized to chaotic oscillator and so on, but it's very simple to define a phase for a periodically behaving oscillator. So I can use actually this very simple equation for all the dynamical system which has a limit cycle in their phase space. But this is actually a very, maybe this is the zeroth approximation. And what about the complications of the main dynamical equation? And the next step to giving a good approximation is how this phase oscillator respond to external stimuli. There is a very simple notion. Consider I have, for example, a neuron, a neuronal oscillator. I have the oscillator is firing periodically. Then I perturb the oscillator with a brief, small amplitude pulse. Before I impose the pulse, the period of the firing is something like this. After I impose the pulse, the interspike interval, or say period, changes. If I calculate the difference between this time and this time, I can actually extract a measure of the response of this neuron, of this oscillator to external stimuli. It's something like a green function if you are familiar with the notion of green function. Is something like a green function for linear systems. For the neuronal oscillator, there are two classes of phase response curve. How I calculate the phase response curve between two successive spikes? I impose a pulse in different instant, and I calculate the response of the system, and in this way, I can extract a curve which is called phase response curve. It shows that if here and here I have two spikes, it means that if external stimuli reach here, the neuron is not responsive to it. But if the external stimuli is here, the neuron is very responsive to this external stimuli. If the phase response curve is always positive, it means that when you have an external positive stimuli, it reduces the period of the firing. Then this curve will be always positive. And if that's always positive, we say that the neuron has class 1 or type 1 excitability. On the other hand, if there are some negative parts in the phase response curve, the neuron is of class 2 excitability. Note that in this case, you are imposing a positive pulse to the neuron, and the period is increased. It's somehow weird, but not very much. So I have two classes of neurons, class 1, class 2, and the notion of phase response curve helps to make a better approximation for defining a limit cycle. The first one is the notion of phase, and this shows, actually this is the first term, linear term of how external stimuli can affect this oscillator. If I want to see the response of a neuron to external stimuli, I should convolve the external stimuli with the phase response curve, and I can have a good approximation when external stimuli is small amplitude, because this is just the linear approximation. Having the phase response curve, now I'm in a position that I can calculate the synchronization properties of two coupled neurons. Consider that I have two coupled neurons, bidirectionally coupled, with a certain type of excitability. With a simple map, this is actually the phase approximation. This vertical line shows that when a stimuli from other neuron reaches to target neuron. Here, one neuron fires. After a time lag, this excitation reaches to other neuron, and with this very simple map, I can calculate the synchronization properties of two neurons. And it's interesting because depending on delay time, I stress that I have two neurons. I consider a delay time in communication between two neurons. The situation is symmetric. The neurons are identical. The connections are symmetric, of the same delay, of the same coupling strengths. In this way, it's simple to show that the in-phase firing will be stable if the slope of the phase response curve is negative. So, for example, with this type of neuron, if delay is in this range, I have in-phase firing. It means that the connections are synchronizing. If delay lies in this region, the connections are desynchronizing, and the two neurons firing antiphase with high phase lag. And actually, the synchronization properties depend on the type of excitability, but this law is true for type 1 or type 2. Maybe I should say here, this is numerical results. It shows the phase difference of firing of two neurons, and this is the slope of phase response curve. When the slope is negative, they fire in synchrony with zero phase lag. When the slope is positive, they fire in almost antiphase with high phase lag. I assume that you know this configuration much better than me. But let's go back. In this figure, we see that for two coupled neurons, for a range of delay times, I have antiphase firing, and for another range, I have in-phase firing. Changing the configuration, it is possible to have always in-phase synchrony. You can just consider that if these connections are synchronizing, it means that these two neurons fire in phase. And if this is synchronizing, these two neurons fire in phase. It's simple to see that as a result, the outer neuron would be in phase. This is trivial. But if the connections are desynchronizing, depending on delay changes, and the connection changed to a desynchronizing connection, and as a result, these two neurons would fire antiphase. These two neurons also fire antiphase, and again, the winged neurons would fire in phase. So in this configuration, almost for all the delay times, you can have two winged neurons firing in phase. I've shown this in this picture. Actually, the results depend on as you can guess, the results are dependent on the symmetry of the configuration. And you have shown that the notion also works for 3 population of neurons instead of 3 single neurons. Again, if there is an intermediate relay neuron in between 2 populations, the outer population can fire in phase regardless of the value of time delay. We had also a contribution in this system. We have shown that actually, while the symmetry of the system is preserved, the results are valid. I have, for example, if you have 3 neurons identical with all identical connections, the results are valid and it's reasonable. But if you change one of the neurons, for example, the middle neuron is different from the 2 other neurons, the system is heterogeneous but symmetric. You can see the symmetry in the system. In this case, the 2 outer neurons will synchronize in phase. Again, you have consider other situations which there is, for example, delay times here and here are different, but they are symmetric. Again, 2 outer neurons can synchronize, but if you break the symmetry of structure, the outer, for example, if you have one of the outer neurons different from 2 other, or in this case, delays here are different from here, you wouldn't have the synchrony of outer neurons anymore. But maybe this slide is the essence of my presentation. What happens for the 3 neurons motif if I connect the 2 outer neurons as well? Let's assume that system is homogeneous. I mean that all the neurons are identical and the connections are also identical. The nature of connection depends on delay, as I told you. If and delay and the phase is secure. I should stress that when I say delay, it is normalized by the period of the fire. So delay 1 means that the delay is equal to the period of the fire. So if I choose delay here, it means that the connection is synchronizing. If the connections are synchronizing, no ambiguity exists because these 2 neurons want to be synchronized in phase. These 2 neurons also, and these 2 neurons also. So all of the neurons will be synchronized trivially. But this is actually the untrivial case is when you choose delay which makes the connection desynchronizing. If the connection is desynchronizing, for this connection, 2 neurons want to be antiphase, and this is true for other connections as well. You can imagine that this want to be antiphase, so this want to be antiphase, and there is a confusion here. So you know the notion. This is called in actually a spin system. This is called as frustration. The system is confused because this component doesn't know how to match its space with other components of the system. In the energy landscape, you can see that if you define an energy for the system, decreasing energy for this connection increases energy for the other connection, and it will be difficult for the system to find the minimum energy of the system. So some interesting phenomena AI. Let's see what happens for 2-neuron system, 3-neuron system, and larger network in this case. Again, I have wrote here, this is phase response curve when the slope is negative, connections are synchronizing. If they are synchronizing for 2 neurons, they are synchronized, 3 neurons synchronized, any neuron are synchronized, it's trivial. And you can see this in simulation as well. And if you average for the larger neuron networks, if you average the activity of neurons, this is called as local field potential in nervous system. This is actually average activity of all components of the system. If they are synchronized, you see a large amplitude activity of the whole network. Periodic, oscillatory, and large amplitude. On the other hand, if the connections are desynchronizing, positive slope, for 2 neurons, it's trivial, you can fire antiphase. For 3 neurons, actually new states emerge. They can be antiphase, in phase, or with actually equally spaced in time with other phase lags. I have shown one of them. Actually, there are 6 stable states for the system when the connections are desynchronized or frustrated system. If you have a large network, actually the stable states of the system increasing exponentially. So it's very difficult to find the final state of the system from simple properties of the connections. So what you see usually is irregular asynchronous dynamics. There is no obvious connection, obvious time lag between any 2 neurons in the system, and the average activity of the network would be irregular, small amplitude, and noisy.
Don't you see like diagonal features in this plot?
Sorry?
You see diagonal features in this plot?
Yes, there are. Actually, in this system, I have not noise.
It's like pushing.
You're talking about this?
And
Or
there,
this?
and then if you go down, you see the same, just fade.
You're talking about this, isn't it? Yes, there are minimums in the system, actually. There are minimums. But there are many minimums in the system. So the system is very prone to noise. So if you have a small amplitude noise, the system switches from this state to that state and will be very irregular. But in this case, you just have a one minimum, and it's actually doesn't feel noise. You know, it's robust against noise. So now again, I stress on the results. For a network, delays are not equal to each other. Certainly, we have a distribution of the delaying system, but if the distribution is narrow, again, the results are valid. This is the distribution of delays. Its distribution is this region, negative slope. You have in-phase firing. In the positive slope of the PRC, there are some sort of irregular firing. But we can say that in a nervous system, delays are almost unchangeable. This is hardware. Delays are hardware. And actually, there are counterexamples. For example, in evolution of the brain, there are some procedures, myelination of the axons that change the delay time of communication between neurons. But in time scale, we are interested, for example, one day, it's actually the delays are constant. But I told you that delay itself is not important. The ratio of delay to the period of firing determines the synchronizing properties of the connection. So we know that firing rate of the neurons in the brain can change easily. If you change the input to the neurons, the firing rate changes. So I have shown here, with fixed delay, if this shows the period of the firing at first, so you can see that I have positive slope and delay determined that the connections are, in this case, connections are asynchronous. But changing input, this is the level of input. If you change the input up to the network, the firing frequency changes, period changes, and in this case, with fixed delay, you would see that the connections change to synchronizing connections. So, simply with changing the level of input to the network, you can change the state of the network. First, it's irregular firing, asynchronous firing, changing input, we can change it to synchronous firing. Now, I just want to give maybe some functional relevance of this finding. Actually, synchronization in nervous system is a very dynamical phenomenon. Rhythms emerge and wax and wane. Sometimes you see them, sometimes you don't see them. And as a very common example, at the beginning of exposure of a sensory to the nervous system, always an oscillation in the sensory system is seen. The very classical example belongs to Gray and Singer. They show that in the visual system, at the beginning of exposure of a stimulation to visual system, you will see an oscillation in the system. It means that transiently neurons are synchronized, show an oscillation on average, and then it disappears. So this is what we call transient synchrony. There are many examples of transient synchrony in nervous system. This is another example, recent example, experimental results. They show something to monkey, and in the primary visual cortex, they see some oscillations, oscillations in the network level. Other examples are present for olfactory system of different species. This is actually a stimuli, exposure of an olfactory stimuli to zebrafish, and they see that some oscillation in network level, and eventually it disappears. Again, another example, you see that here is raster plot I showed you. You can see that here neurons are firing in phase. In here, the neurons are actually asynchronous, and maybe you can guess that how we can explain this phenomenon with our model. You have just one network, delayed couple, and you have a simple stimuli. You just change the level of stimuli, and at first you have not any oscillation in the network level. The response of the network is noisy. Then, changing the stimuli, the network would be synchronous, and you see oscillation in the network level, and again it disappears when the stimuli is back to its initial value. Another explanation can be interesting. There is a procedure called selective attention. Consider that you are in a cocktail party, everybody is talking with each other, but you can concentrate on for example, two persons are talking in a corner of the room. You can ignore all the inputs, all other inputs, and just concentrate on two persons are talking with each other. It means that brain is capable to prevent some inputs to pass through the nervous system and just select some of them. We have some explanation. For example, if you consider this is the input, it doesn't change, but you have a control input to the system. This control input comes from another network in the network system. This control input can actually determine if the data can pass through the network or we can prevent it. If the network is synchronized, it can pass the data, and if it is desynchronized, it prevents the data to go to upper level. Maybe you remember that. I told you if a network is synchronized, it can excite the other levels of nervous system. But if the network is desynchronized, it cannot excite the other levels. So this can be as a procedure that we can actually filter the inputs. Some of the inputs can pass if this here, and I can prevent the inputs from passing from the network on demand. And the other point is that crucial point, decisive point, is delay. If we ignore delay in the communication between neurons, if I change the level of input, simply the frequency of the firing of the neuron changes, but the synchronization properties does not change. So it's a very trivial example with instantaneous couplings. But if you consider delay, if you actually don't ignore delays in communication, the system will show non-trivial results. This is maybe another actually numerical experiment. We have shown that here. I told you that if this is synchronized, they can excite actually the output neurons. We have examined that. I have a network. The network excites just one neuron in another level. You can consider there are many of these output neurons in that level. But I have shown that changing the input to this network, you can switch the output neuron to fire or not fire depending on the synchronization or desynchronization of the intermediate network. So, no conclusion for now, but maybe you just can say that delays are usually literally bad work. You have a take commitment and you have delay, it's not good, but maybe evolution has used delay for a richer dynamics in the nervous system as a model of my time. So I finished you now. Let me say that this work, my former master's student, he is now a PhD student in Germany, and my PhD student he defended about 1 month ago. She is looking for actually a postdoc now, but maybe in Iran, and you know Leonardo better than me.
Questions? Comments? I mean,
is there any typical relationship between the range of delays in some nerve, some brain, and the period of the neuron? So is there some range, for example, restricted to 1/2 of the period, or covers many orders of magnitude? So what is the range of delays compared to typical ranges of oscillations?
Actually, I had a maybe I can show you.
Just to say if evolutions are selected some range, or just for every function it should be different.
Yes.
So this is the delay, but it means the period to compare with.
Actually, if I can say that if the neurons are nearby, it's very naturally. If they are nearby, the delays are small, but if they are far apart, they are larger. For example, you can see that delays can amount to tenths of milliseconds. But what you're asking is that how maybe evolution has chosen some range of delays to...
Yeah, how is this range related to the range of periods? If there is any relationship.
Maybe I should think about that. Maybe
I think you have oscillations in the range of 0.1 to 200 Hz. That is typical oscillation range in the
yeah.
brain.
Yeah.
So very low frequency to very high.
And interestingly, the delays change in evolution. When you're infant, the delays have some other values, and when during the evolution, there are some procedures that change the delay for an adult. So for an adult, but it's somehow fixed. But again, there are some, I have seen some procedures that change delays. I don't know, maybe they have functional roles, but it's difficult to say.
Yeah.
Have you examined the stability of the data stabilities in a large networks? You have told us. Have you examined the stabilities of them?
Actually, we have imposed actually we have added noise to the system. Yes, with small amplitude noise, you can see that there is no stable state in the system. So we can guess that actually the minimals are very, very, they're not very much stable. They are locally stable, but with a small amplitude noise, you can switch from this state to that state.
By looking at these numbers, it is clear that the delays are first considered between two different layers. So I guess that there is also some intra-layer delay, but that's not as important as the inter-layer delay. And so that's one thing. And the other thing is that the delays between layers still they are very different. So for instance, layer 6 to LGN is between 1 and 44.
Yes.
It's a huge difference.
Yes,
so
yes.
the delays you consider in the model are basically all the same. So to which extent the fact of having both interlayer delays, which could be small but they might be different, and then different a variety of interlayer delays could be also important.
Yes, actually, as you say, there is two peaks in the distribution of the delays. Maybe it means that some of them are for interlayers and for the local networks, and some of them are between layers. And in each scale, actually, what we say is you can consider each oscillator as a group of oscillators. So the results may be also valid in different scales, you know, for different regions of the brain instead of different individual neurons. But as you say, maybe in the second case we have a larger distribution.
Yeah, but you consider the distribution of delay. The last results were for delays that were...
Yes, but frankly saying, we haven't compared that with, you know, very well with experiments and real values. So that's just for now, it's just like,
Any other question or comment? Well, if not, thanks again. Gracias.